Good morning. Let me start by thanking the organizers for giving me this opportunity to give this talk. There is a mistake in the date, but today is 17th. So anyway, let me start. So the work I'm going to discuss here is done with one student at IISER Pune, Hunarveer Singh, and another student at TIFR Hyderabad, Chandrasekhar Iyer. Chandrasekhar is here, Hunarveer is not here, and the faculty colleague at Hyderabad is Mustansir Barma, who is also here. And this paper is accepted for publication, but we don't know if it will come this year or next year. And there is some details available in this archive version. Okay. So the problem I would like to discuss has been of interest in statistical physics for a long time, and it has three ingredients. One is diffusion on a percolation network. The prototypical model is DGen-Ant, is introduced in 75. And there is this stuff, bias diffusion in disordered media. These are the review articles. Each of them cites some 500 or more references. So, there is a lot of work. And there is asymmetric exclusion process of interacting particles. This one has been studied a lot as a prototypical model of driven systems, TSEP or some such thing. We will study it on percolation clusters, not in 1D. And that is the difference. This work is a takeoff on some long old work of Barma and Ramaswamy in 85, where they studied exactly the same model. But then, they in the end they said that it would be nice to study this further, and they didn't do it at that time. And so after a gap of some 30 years, we decided to take up the problem again. Okay, so let me give the definition of the model. We consider a d-dimensional lattice with periodic boundary conditions. A fraction q of the sites are removed at random. So this is the percolation cluster. We will take q to be small, less than the corresponding percolation threshold, so that you have an infinite spanning cluster. And we place hardcore particles on a fraction rho of the sites available. This system evolves in time by Markovian evolution. Each particle tries to jump to a neighboring site with fixed rates. The jump is allowed only if the site is present and empty. Okay, you cannot jump to a not present site. So movement occurs only on the percolation cluster. And there is a biasing field that makes steps along the field more likely than against. Okay, that's all the definition of the model. This is a picture. So you take a big lattice. This is sort of a part of the big lattice. The sites which are absent are denoted by black squares. They are removed. The rest of the stuff is sites which are present. But there is a percolating cluster. There could also be finite clusters of occupied sites. So those we don't worry about because the diffusion on them is rather trivial. So you look at this pink cluster, which is part of the infinite connected component. And some sites there are occupied. And so these are the red sites. And these red sites are, let us say, part of the finite cluster, and we don't worry about them. Okay. Okay, in the stochastic evolution, we pick a particle at random, pick a direction for attempted jump with probabilities as shown. So 1 plus g by 4 and 1 minus g by 4 and 1 by 4, 1 by 4. And make the jump if allowed, else stay put at the same place and repeat the whole thing again and again. So this is right in continuous time right now. So we are asking what is the long time steady state of this system?
But Deepak, just clarify, the preferred direction is globally the same?
Yeah, it is the same everywhere. So on the spanning cluster on an L by L lattice with periodic boundary conditions, there is a unique long time steady state. In the steady state, the particle moves along the backbone, then goes into a side branch, then eventually comes out of it, moves along the field, then gets trapped again, and so on. So it keeps on going into backbone, side branch, backbone, side branch. And statistical properties of a marked particle's trajectory for long time are the same for all particles. Okay, so we don't have to worry about that. So you can look at one particle's trajectory and ask questions about that one. And a particle will visit all the sites on the spanning cluster many times and spend a non-zero fraction of total time at each site. This is a finite cluster, L by L. Okay, so we distinguish between time spent in the backbone and in the side branches. Time spent in the same side branch between two steps along the backbone will be called the waiting time in the side branch. Okay, the question we ask is this: in the steady state, we pick a particle on the spanning cluster at random. What is the probability that it has been in the same side branch for the previous t time steps? And for particles on the backbone, the waiting time is 0 by definition. So this t, of course, is a random variable, and we like to find out the probability distribution of the waiting times. That is the problem we are studying. Summary of results. The system shows dynamical heterogeneity with, some particles move faster along the backbone and some particles are somewhat stuck. So there are regions where there is average velocity is big and there are regions where it is small. Okay. The distribution of waiting times in side branches has a very wide distribution. Probability of waiting time in the same branch bigger than tau goes as exponential minus a square root log tau. So this is slower than any power law. The probability distribution of log tau shows multiple well-separated peaks. And the coarse grain velocity autocorrelation function of the, so you can take a tag particle. So this is Markovian dynamics of jumps. So there is no velocity as such. But if you take an interval t, you can define an average velocity in the interval t and keep t fixed, but then calculate this average velocity at two different windows. Then this correlation function also decays very slowly, exponential minus a square root log t. So as you know, this for the Einstein diffusion model Brownian motion, there is no velocity correlation function. For hardcore particles which diffuse around interacting with other particles, there is a hydrodynamical 1 upon t to the power d by 2 kind of tail, and this tail is much slower. So at zero bias, there is a phase transition as a function of density, and the probability that the net displacement is 0 goes like t to the power minus a by 2, where a is d by 2 for rho less than rho c. This is normal diffusion behavior. And this a changes to a function which is a value which is less than d by 2 for rho bigger than rho c, and this a then changes continuously with rho. Okay, so earlier work for small fields, we have a mean drift along the field, and there is a mean current in the system proportional to the field. And for infinitely strong fields, there is no current possible if P is less than Pc and the directed percolation threshold. So it was realized by us in 1983, long ago, that the average drift velocity of non-interacting diffusing particles on a percolation cluster is non-monotonic function of the field and actually vanishes for all field strength E bigger than E star. So this is the argument here is important because we will use it again. So this is, let's say there is a single particle moving on this percolation cluster. I'm plotting the average velocity averaged over a very long time as a function of field. Initially it increases with the field and eventually it decreases and actually becomes 0 at a finite value of the biasing field. Okay, this behavior is due to trapping of the diffusing particle in side branches along the field. The particles get trapped in a side branch and has to move against the field to get back to the backbone. The average trapping time in a side branch of depth d is 1 plus g over 1 minus g to the power d. And on the other hand, the probability of a side branch is a decreasing exponential in d. So if you want to calculate the mean trapping time, depending on the ratio of this product of these two numbers, you will get a divergent series or the convergent series. So for 1 plus g over 1 minus g bigger than exponential 1 upon Cp, the mean trapping time in a side branch diverges and the mean velocity becomes 0. So this is the finite value of the bias. Okay, so simple cases with interactions. So what happens if you put in interaction between particles, hardcore interaction? For weak fields, there is a mean current in the system proportional to the field for all densities less than 1. In the limit of infinitely strong fields, G equal to 1, there can be no current if P is less than PC because there are no directed paths. So that part is kind of trivial. Even for P bigger than PC, suppose the field is infinitely strong and density of particles is low enough, then all the added particles eventually get stuck in dead-end traps and there is no current. They go into side branch, they cannot come out, and eventually all the particles end up in these traps and there is no current. Current is possible only if the density is high enough so that there is some particles left in the backbone after all the traps are filled. Okay. Now let us discuss the behavior. Strong fields, but not infinitely strong fields. With 1 minus g is much less than 1. G is near 1, but not 1. In this case, if the density of particles is small, the particles get trapped inside branches, but there is a small activated current in the system and there is a small probability that the particle will be able to get over the potential hill. So now the particles still get trapped, but then they can come out because the field is finite. And so the average current goes like 1 minus g over 1 plus g to the power h, where h is the smallest barrier height. So all these particles kind of go into some traps. Then there might be some particles which are trapped, but they have small height. They will come out and get into some trap which is much deeper. And eventually, there is one particular value of h such that all the traps which are bigger than this are filled and all the traps which are smaller than this are typically empty. And so this h will determine the average current. And of course, h is an integer, but as a function of density, this will vary discontinuously. Okay, so you get any infinite number of changes if h, but this is in this limit, g goes to 1, otherwise this thing doesn't have any singularity. Okay, so the general case of interacting particles with g less than 1, the interaction between particles gives rise to two competing effects. The particles get stuck in side branches, but this makes the effective depth of the side branch less than 1, less smaller for the next incoming particle. And the second thing is that the particles that are deeply buried in a side branch below, other trapped particles, find it even harder to come out and have a much increased trapping time. So one of them kind of makes it more likely to, the side branch is less effective and this one increases the trapping time. The net result is that then there is non-zero average current, but the probability distribution of trapping time in side branches has a very fat tail. So we want to study this distribution, and there is a sort of first problem when we wanted to understand what happens if you have a single branch closed at one end, open at another, the field is biased towards the end, and the particles can enter and leave this side branch. So there is a rate p at which they enter, rate q at which they leave. Then what happens in this? Okay, so these are the rates inside. So the number of particles in the side branch can keep on varying because they can enter and leave. And there is a 1 plus g is the w times 1 plus g is the probability of leftward step and 1 minus g times w to the rightward step. At the end point, particles can enter or leave, but we imagine that there is another site here which is sometimes filled and sometimes empty, which is the backbone. And so there is a rho 0. So in this simulation, you just always assume that the rate at the end will be w into 1 minus g, and this is the probability this site will be empty, and vice versa. Okay, so in this case, The exact steady state probability distribution is a product measure. Each site is independently occupied with activity ZD at site D being Z0, 1 plus 1 minus G to the power D. This just comes from detailed balance. Sites at depth bigger than D star are occupied with probability near 1. So for any Z0, there is a particular value of D such that this whole product becomes much bigger than 1. And that determines this rough number D star. So if there is a big trap, you can say all the sites below D star are filled, above that are empty. And this D star depends on rho 0 and G. The escape from a branch of particles at depth D bigger than D star involves emptying all the sites to the right. And this has a free energy barrier, constant times D square minus D star squared. And escape time goes as 1 plus G over 1 minus G to the power D squared minus D squared, D star squared. Okay. So now this is sort of a heuristic argument, but it actually captures the essential point. And now there is a little bit of detail which I'll show. So we can define a transition rate matrix W for this chain. And now we define a submatrix Wj consists only of configurations in which there are more than J particles. So you take the full matrix and delete rows and columns corresponding to less than J particles. Then if you, so this is a subspace over which this smaller matrix Wj works. If we start with a configuration C with more than J particles, the probability that the system has remained in this subspace throughout this time, up to time t, is Wj to the power t multiplied on C sum over all possible in final states. Okay, because the sum of rows, sum of columns in the W will not be 1, and so this probability decreases exponentially eventually. So using this for different J, we can determine the probability that the jth particle from the left has not left the system. Okay, if we take C according to the steady state measure, but we restrict that the number of particles is exactly J in C, then the rightmost particle is at 1, and this gives the probability of that the rightmost particle is 1, then this gives the probability that the waiting time of the particle is greater than T, given that it just entered the side branch in the steady state. Okay, so then this W matrix you can write down. So for 10 by 10, L equal to 10, this is some 1000 by 1000 matrix, not very big. And then you can calculate all these Wj. And then we want to evolve this system. Okay, but we want to evolve it for pretty long times. And if you evolve step by step, it will be very hard. But actually, if you want to calculate W squared, W4, W to the power 8, W to the power 16, those can be done by single multiplication of the lower order. So W to the power 2 to the power n can be easily determined by just by squaring. So this we do, we evolve for T up to 2 to the power 200. And then you can, so this determines the probability that the particle stays up to time t, and then you can determine the distribution of the, this is the probability that the particle stays up to time t and as a function of log t. And interestingly, it has these multiple peaks in the log t variable. The width of these peaks is of the order of 3 or 4. It depends on the fields and stuff, but the spacing between them is much bigger. So they are widely separated, but there will be some events in between, of course. It's not fully excluded. And this is the interesting result of multiple peaks. In fact, in the thermodynamic limit, the number of peaks is infinite, and the spacing between the peaks becomes bigger and bigger, while the width of the peaks remains finite. Okay. So we see that particle at depth D, the logarithmic of the waiting times is sharply distributed random variable with position of peaks widely separated for different D. And you can calculate the cumulative distribution. So this is the probability that the time is bigger than T as a function of square root log T, and you see a nice simple behavior. So all these particles have a depth bigger than some J, and these are bigger than j plus 1, bigger than j plus 2. So each peak corresponds to particles which are buried at some depth d, and deeper particles have a bigger depth by several orders of magnitude. So here the fitting function is used to fit this, which was very simple. We just use the floor function and log t, square root log t divided by some normalization, which you can check has to be this one. So there is only one parameter c, and you see it fits the data pretty well. Okay, so now, so that was a single branch, and a single branch is not very respectable in statistical physics. You say, why are we studying some system with only depth 10? So, but you can take a regular Coombe structure with side branches of the same depth, and the analysis actually kind of goes through, though it is not rigorous now. But if you can compare the distribution of the waiting times in this structure, which is very big, in the backbone is very big, it matches very well with the distribution we calculated for a single branch, because the time spent in one side branch is more or less independent of the time spent in a second side branch. They are not fully independent, because when the particle comes out, then it has a bigger chance of going back in again into the same side branch. But they are nearly independent, and this is a picture of the Monte Carlo simulations of the regular Coombe for depth 1, 2, 3, 4. 1 is here, 2, 3, 4, even for just j equal to 4. And the cumulative is like this, and there is a very good match between the theory as determined by one branch and the actual simulation with many branches. Okay, so this is G is 0.5, ring size is 100, data is averaged over 10 to the power 5 MCS. But there are many particles in the simulation. There are some 300 particles. Okay. So one may extend this result now to a random Coombe, where the length of the side branches are different, and probability of branch of depth d goes like exponential minus CD, and the probability the waiting time is bigger than t is roughly equal to the fractional number of sites with depth d, such that their trapping time is bigger than t. And so we get this result, probability of waiting time bigger than t is minus a square root log t. Okay, and now we go to the percolation cluster. So percolation cluster is a bit more complicated than random Coombe, but this point that the distribution of side branches of depth d goes like exponential minus d is still true, and this result is still true, and this we have checked by simulation. So here is the probability on a spanning cluster of a percolation network in log t, and the graphs for different value of the scaling variables nearly coincide. But you know, this is in Monte Carlo we are restricted to times of order 10 to the power 5, 10 to the power 6, while in the theory we had used 2 to the power 200. So you cannot get the asymptotic regime very well, and this fit is not perfect, but it says that the theory couldn't be very, very wrong. Okay, so now just some final comments. Dynamical heterogeneity. In glassy systems, one often talks about dynamical heterogeneity. Here there is, this is also true, but the position of these regions are not changing with time due to the quench disorder. And particles get trapped due to hardcore interaction. And this gives rise to a simple classical mechanical system to study many body localization. The many body localization is happening here, but it is in classical mechanics. It doesn't have any quantum mechanics. Okay, the second thing is that if we take a fixed interval t and determine the average velocity of a tagged particle in the time window tt plus t, this is a random variable, and its distribution is like this. There is a peak near 0. There is some probability that there are negative values also, but this peak is near 0. And then there is a broad maximum. If you increase t, the maximum shifts to the left. The value of this peak also shifts, decreases, and this becomes a bit sharper. But it remains quite broad, and this peak is quite big. and it decreases very slowly as exponential minus square root log t only. Okay, slow decay of velocity autocorrelation function, this I will not discuss in great detail, but if a particle is trapped, then its velocity is different from the mean velocity by a significant amount, and it remains that way even at later time because it's still trapped. And so the velocity autocorrelation function has the same kind of decay. And finally, let me just mention the spectrum of relaxation time. This matrix, if you write down W, it has a gap and it doesn't show any of these long time scales. And that point is very simple because if you want to determine the residence times, you have to tag a particle. If you tag a particle, then the space of configurations becomes much bigger. And this bigger matrix will have slow relaxation scales, but the original matrix W with identical particles shows no such thing. So approximately n of the nearly degenerate eigenvalues of the bigger matrix correspond to eigenvector 0 of W because the tag particle can be any of the n particles. And then this subspace will show the scale discussing. Okay, so this is the summary. The distribution of sojourn times in this asymmetric simple exclusion process is very broad. For any time scale of observation, there is a significant fraction of particles that are localized in the same branch for the entire time. This fraction is quite robust and very slowly decreasing function of t. This is a typical behavior, not a probability of rare events. So if you just take a cluster, and you will find that let us say 10% or 20% of the particles have been there for the last 10 to the power 8, 9, 10, 12 time steps. Okay? And similar behavior in glassy materials is called dynamical heterogeneity. This I already said. And similar deeply buried grains have large escape time. That kind of problem people have studied in the context of sand piles and rice piles and stuff. And there is some earlier work which is somewhat related but not the same. Okay, so let me stop here.
Is different.
You can, the problem, the way I defined this bias was along X direction, but you can take the bias in any direction and all the results continue to hold good with minor changes of coefficients. So it doesn't matter. The periodic boundary conditions hopefully do not affect this result. You know, all these results about the steady state are for particles. You pick a particle, what is its distribution, that will not depend on the periodic boundary conditions assumed.
So the second part of your talk was about these very precise calculations of
Yes.
first one and then using that to build a scaling theory for the comb or the random comb, right? But the first part of your talk had a whole bunch of statements which were the final results. The gap that I'm also confused about is in this picture of backbone and side branches.
Yeah.
Some of the side branches can be against the field, some along the field.
So the ones
That's
which
what
are
he's
against
also
the field
asking, I
don't
think.
matter.
Okay.
They don't do anything much.
And the statistics of these side branches then comes from percolation theory.
Yeah, so half of them are along the field, half of them are against the field, and the ones which are against the field do not matter.
No, so in what sense is it like many body localization? So is like here the parameters are, let's say, density and the electric field, right? So is do you see like metallic to, if you look at the conductivity or current, does it show a metallic and insulating transition as a function of density?
Yeah.
And that's like interaction.
Yeah. So that is so. Yeah, so here, you know, sometimes you can find an activation HN, you can see that for small temperatures, there will be no conductivity, but if the temperature is increased sufficiently, then the particles will start. So it's an activated current. It's not a sharp phase transition, but the activation energy has a discrete jumps, just like Fermi energy in systems will show discrete jumps.
Deepak, I got confused by these sojourn time distributions. So all the peaks are the same height, but normalization is assured because they're farther and farther apart.
This is an effect of the single side branch because there is one particle, the number of particles at depth d is independent of t, it's 1 by L.
Oh, I see. Have you any speculation as to what would happen if your particles, the bias wasn't in a fixed direction, but like Chandan's work, each particle has its own personal direction which it keeps forever?
So no,
Let
we
us
have
say
not studied
uniformly
that
distributed on
problem.
the
That
four
will
directions
be,
of a square lattice, something.
no. So that problem is more interesting. It has extra phases, there are the jammed phases and stuff.
Right.
No, that's an interesting quantity we have not studied.
Okay, let us thank Deepak again.
Okay.